Welcome dear students. In today's lecture we will covering the analysis and design of the beams, singly reinforcement beams. So basically we have divided the beams into two types, general beams, that is the one is the singly reinforcement beam and the doubly reinforcement beam. So as you know that beam is a flexural member. So basically we can provide the reinforcement in that beam to resist the tensile stresses, because the concrete is very weak to resist the tensile stresses coming on that beam. So for that we provide the reinforcement. So once when we provide the reinforcement in the beams, we can easily see that beam we have the cross sections we have like this, if beam. So in that case we can easily see that if there is a one axis which is called the neutral axis, this axis divides the section into two parts as per their capacity. So first section is the section is zone is the term as the compression zone, and below that neutral axis the zone is termed as the tension zone. So when we are talking about the compression zone and tension zone, it is as I already told you that it divides by the neutral axis. So how it defines that the compression zone is above that neutral axis or below the neutral axis? So for that we have to know that it depends on the what type of beam it is. If it is simply supported beam, so basically what happened that when that beams supposed to bend, in that case what happened that if the beam is simply supported, so and beam has supposed to bend, in that case what happened that the beam bent like this. If this is the beam, simply supported beam, and it bends, so it bent like this, then what happened, the topmost surface is in compression and the bottom portion of that beam is in tension. So that is why we can say that in simply supported beam the upper section is in compression zone and below section is the tension zone, and that there is one axis which is neutral axis which divides the section. The vice versa in case of cantilever beam, the tension zone is upper side and the compression zone is on the below side. But now I am coming to the what type of beam. So if we only provide the reinforcement into the one zone, that is the tension zone, if we provide the reinforcement only the one zone, then the beam is termed as the singly reinforced beam, because we are only providing the reinforcement into the one zone of the beam. So that is the why the singly reinforcement. If we provide the reinforcement in tension zone as well as in tension zone as well as in compression zone, so then in that case we termed that beam as a doubly reinforced beam. So now I am coming the technical terminology regarding the beam. So actually we have the cross section like this of the beam, in which you can see the one dimension is the width that we term abbreviate by small b. Then we have the overall depth, that is the capital D, but for calculation we use the term small d, that is the effective depth, So how we can calculate the effective depth and what is this? So effective depth is the from the compression phase to the up to the center of the tension reinforcement, that depth is the effective depth, and for this we require the effective cover. So for effective cover, how we can calculate the effective cover? So we can calculate if this is the bottom portion of the beam, so from here to here we have the clear cover. This is distance from the outermost to the reinforcement and the outermost to the section of the beam. So this is called as the clear cover. So this is called the clear cover. If we go up to the center of that reinforcement, so in that case we have to add the radius of the into the clear cover, then we get the effective cover. So this d dash is termed as the effective cover. So in this case we can easily say that the effective cover equals to clear cover and half of the diameter of the bar. So this is how we can get the effective cover. If we subtract this effective cover from the overall depth, then we get the value of effective depth. So this is the some terms which we will use during the analysis and design problems. So basically now if I come to the numerical problems, then how we will analyze or design the problem of singly reinforcement beam. So basically we have the two type of problem. One type of problem we call the analysis of beam, and second type of problem is the we call the designing of the beam. So analysis of beam is that portion in which we know the section, we know the reinforcement. Now we have to check whether this given beam is good or not, it can resist the given load or not. So that we have to check in terms of moment of resistance. Okay, so in that case, so that beam is, in that type of problem we call the analysis problem. And second type of problem is the design of beam. In that case we can easily see that if in that case we don't know the dimensions, we don't know the size, we have to decide the size, we have to provide the reinforcement. So all that kind of problem we call the design of the beams. Okay, so these two type of problem generally we have. So now when I coming to the numerical, these problem into the numerical, then it converts into the three type of problem. First type of problem is a purely analysis problem, in which we have the size of the section, we have the reinforcement, and we have to check the given, we have to calculate the moment of resistance, and we have to check the whether section is satisfy or not satisfy as per the codal provision of IS 456. Similarly, second type of problem is the partially designed problem, in which we have the dimensions but we don't know the how much is the reinforcement. So in that problem we have to provide the reinforcement. So that is the second type of problem, and that is the partial design problem. Okay, and third type of problem is the purely design problem. In this we have we don't know the dimensions, we don't know the reinforcement, so we have to first decide the what should be the dimensions, and after that we have to provide the reinforcement. So that type of problem is the fully designed problem. So that in this topic we have such three type of problem, which first belongs to the purely analysis, second is the partially design, and third one is the purely design problem. So now I am coming to the first type of problem. So first type of problem, as I already told you, that we have to calculate the moment of resistance. So what kind of information you have in the question with you? You have to calculate the moment of resistance. So you have to know that what the information you have in the question. That is, first one is the dimensions of the beam. If the dimensions of the beam I am talking, then it means you have the width of the beam, or you have the capital D, that is the overall depth, or if effective cover is given to you, then you have the effective depth. So that is the dimensions of the beam you have. This is the first information which you required for the calculation of moment of resistance. Second type of problem, second is the area of the steel reinforcement which you have provided into the tension. For that we have using the abbreviation AST. So we know the cross sectional A, we can we know the number of bar and diameter of bar, then we can easily calculate the AST. So how can we calculate? Consider that number of bar is the N and the diameter is the phi. So in that case, what is the AST is? In that case the AST equals to, in that case the AST, area of steel in tension zone, equals to number of bars, and we have to calculate the cross sectional area of that bar. So we know the cross sectional area of the bar, pi by 4 phi square, and the number of bar is the N, so we can easily calculate the area of steel. So this is the second requirement we have for the calculation of moment of resistance. And third type of this is what kind of material we have. So generally in RCC beam, as we know that we are majorly using the two materials, one is the concrete and second one is the reinforcement. So for concrete, we know that concrete we will represent the grade of the concrete like M20, M25 like this. If 25 grade of concrete, then we write like M25 grade of concrete. Okay, so 25 is the characteristic strength of this of that concrete, which for that we will using the FCK, and that is the 25 Newton per mm square. So this is how we can calculate the characteristic strength of the concrete. So we know the grade of concrete, so easily we can calculate we can easily find out the grade of what is the characteristic strength of that concrete. And second is the grade of steel. So generally we have the three type of steel. The first is the Fe 250, second is the Fe 415, and third is the Fe 500. Fe 500. So from this we get the yield strength of the steel, that is the Fy. If we have the Fe 250, then the Fy equals to 250 Newton per mm square. Similarly, if we have the Fe 415, then the Fy equals to 415 Newton per mm square. If we have the grade of steel Fe 500, then the yield stress Fy equals to 500 Newton per mm square for that steel. So this is how the grade of the material help us to find out the FCK and Fy. To solve these problems, we have the one document which also allowed in the exam, that is the IS 456. this IS 456 help us. It is having the all the specifications which is required for the designing and analysis of a beam or of a RCC structure. By using this document help us, and this document is also allowed you can use it in the exam. Okay, so now I'm taking the first type, this numerical problem for this type of problem. So this is the, before going to numerical problems, we have to discuss what kind of design steps we have for such type of problem. So for that we have the first step in which we have to calculate the neutral axis. As I told you, we have the beam, or consider that beam is the simply supported beam. Okay, so we have the one axis, that is the neutral axis. So we have to find out the depth of this neutral axis. So this is the x, we abbreviate the depth of this neutral xu. So we can easily calculate. For this we have the formula. This is the formula we have: xu by d equals to 0.87 f by ast, 0.36 fck b and d. This is the formula we have, and this formula is given to you in the at the page number 96. Page number 96. So from there, now what we required in this, now 0.87 is a number, f by we already know, because we know the grade of steel. So we easily know that f by we have already. Now ast we already know, it is also given us to in the question. Then the fck is the characteristic strength of the concrete, it is also we can obtain from the grade of steel. And after that, width and depth, it is also we know from, it is also given us in the question. So but you have to remember that this small d is the effective depth, not the capital depth. So for that, this small d equals to capital D minus small d dash. Capital D is, this is the effective depth, this is the overall depth, and this is the effective cover to the tension reinforcement. So this is how we can calculate the depth of the neutral axis. This is the formula we have. While calculating, you also take care, because this is a numerical subject, so you have to also take care regarding the units, what units you are putting and what the unit you are getting. So when we are putting all the values in, if we are putting the values of f by Newton per mm square, ast in mm square, fck in Newton per mm square, b and d in mm, then we can find out this xu in terms of we can find out this xu in terms of mm. Okay, if we are calculating xu by d, then we can easily understand that there xu is again in mm, d is again in mm, so there is no unit for xu by d. If we are talking about the only xu, that is the depth of the neutral axis, in that case the unit for that is equals to is the mm. First step. This is the second step. In first step we have calculated the actual depth of the neutral axis, and second step we have to calculate the limiting depth of the neutral axis. So that is the xu max. We using the word xu max here. So now here this value depends on the grade of the steel. So we have, as I told you, that we have these three type of steel: Fe 250, Fe 415 and Fe 500. So for that we have the value of xu max by d is 0.53, 0.48, 0.46 respectively. So again these values are available at the page number 70 of the IS 456. So this is how we, in first step we have calculated, if we have calculated xu in first step, then we have to calculate it in a second step, we have to calculate xu max. If we are calculating xu by d in first step, then we have to calculate the xu max by d, then we can compare in the third step. So in third step what we have to compare the both the values, that is xu and xu max. So xu and xu max we can easily compare. On the basis of that we define the section, that if the depth of neutral axis is lesser than the limiting depth of the neutral axis, means xu is lesser than the xu limiting, then the section is termed as the under reinforced section. In that case we termed that section as the under reinforcement section, and moment of resistance we can calculate by using this formula. Again this formula is at the page number 96 of the IS 456. So this is the first case. In step number 3, if this value, this condition not arrive, we arrive the condition like this, that xu is equals to xu max, or xu by d equals to xu max by d. In that case we term the section as the balance section. For that, in that condition we can calculate the moment of resistance by using this formula. Again same, this formula we have at the page number 96. Then after that, if xu is greater than the xu max by d, xu by d is greater than xu max by d, or xu is greater than xu max, then we call this section is the over reinforced section. So in this condition, code, the specifications given in the code IS 456 that says that we can't design the over reinforcement section. In that case, you have to redesign the section. So we doesn't require to calculate the mu. So this is these are the steps to calculate the moment of resistance to analyze the first type of problem, that is the purely analytical problem. So now I will take the numerical. This is the one question I have, in which I have to find out the determine the depth of the neutral axis. Depth of the neutral axis, in which the beam size is given 250 mm and 450 mm is the effective depth we already given. After that, we are providing 3 bars of 20 mm diameter. So now this is asking the what type of section. What type of section means the examiner is asking us that we have to find out the given section is the under reinforced section, balanced section, or over reinforced section. So okay, and after the grade of the concrete is also a grade of the materials, that is the for concrete is the M20 and Fe415 for the steel is given to us. Now whenever you start the numerical in this subject, in this problem, before solving the problem, I just want to tell you the one thing, that whenever you go to solve the problem, you just start the solution writing the given data first. After that you start the solution. Okay, why I'm asking you to write the given data first? Because if you want to minimize the problem of units, if you have any confusion of units, you can, if you writing the given data first, then you can easily outcome from the any problem of units. So that is why I'm asking that initially you have to write the unit first, then you start the solution. So now I'm taking the problem. So now this is the problem we have. Determine the depth of neutral axis of a beam 250 mm wide. Okay, so 250 mm wide means the width of the beam is the 250 mm and 450 mm is the effective depth. Effective depth, it means it is the small d, is reinforced with 3 bars of the 20 mm. So 3 bars of 20 mm means that it is the 3 bars of 20 mm diameter. So AST, area of steel in tension zone, that is the 3 into pi by 4 into 20 square. So to check the type of you also first you need to find out the depth of the neutral axis, and after that he's asking also check the type of the section. So type of section means we have to find out the given section is under reinforced, balanced section, or over reinforced section, and at the end the grade of the materials given to us, that is the M20, that is for concrete, and Fe415, that is the for the grade of the reinforcement. So this is the given data we have. The width we have the 250 mm. First it is given to us. After that, if small d effective depth we have, that is the 450 mm. AST 3 bars of 20 mm diameter we have, so we can easily calculate the AST. Then M20 and M20 grade of concrete we have, so we can easily say that characteristic strength for this concrete is the 20 Newton per mm square. And the Fe415 steel we have, then the Fy yield strength for that steel is the 415 Newton per mm square. So this is how I start the solution, first writing the given data with the units. Now first depth of the neutral axis I have to find out. So I easily know that in the design steps I already know that what are the how we can calculate the depth of neutral axis. For that we have this formula, which is also given to you in the code at the page number 96. That is the formula that XU equals to 0.87 F by AST over 0.36 FCKB. Okay, so in this question we have all the values. Fy we have 415, AST we have, okay, FCK 20 Newton per mm square, B is we also have. So we put all the values and calculate, and easily we can find out that is the XU equals to 189.05. So this is the actually depth of the neutral axis. So this is the first part of the question. And in second part, the asking that we have to find out the type of section. What type of section? So for that we require the limiting value of the depth of the neutral axis. So we know for the Fe415 the XU max by D, this ratio equals to 0.48. It is also given to you at the page number 70, as I already told you. So now we compare both the values. You can see that XU we have, that is the 189.05, and XU max we have, that is the 216. So now we can easily see that this value is the greater than the 189.05. So now we can easily see that that XU is the lesser than the XU max. So we can say that this section is the under reinforced section. So in this question up to this, if they ask the moment of resistance, so for the under reinforcement section, whatever formula we have, for by using that we can calculate the moment of resistance. But in this question they are asking only for the depth of neutral axis and type of section. So this is the end of this question. This is the second type of problem we have. In this we have to find out the moment of resistance of a beam. Dimension is given 250 and 350 mm. Now 250 mm is the width and 350 mm is the overall depth. There is no mention that this is the effective or overall depth, but if it is not mentioned, then we consider this depth as the overall depth. It means it is the capital D we have. Then the area of steel consists of 3 bars of 12 mm diameters placed at a distance of 40 mm from the bottom of the beam. So from 40 mm bottom of the beam, it means it is the clear cover we have. Okay, so we can now 350 mm is the overall depth and 40 mm is the clear cover. So now, and diameter of the bar is the 12 mm. So now first we have to calculate the effective cover and then we have to calculate the effective depth. And M20 and 415 grade of reinforcement and grade of concrete and reinforcement we are using in this. So now first we writing the given data. So B is the 250 mm we have. After that D we have, that is the 350 mm. Clear cover is given to you 40 mm and the diameter of bar is given to you 12 mm. So first we calculate the effective cover. So this is the clear cover, this is the radius you can say of the bar. So this is the radius, this is the clear cover. So this is actually, now it is effective cover. So and this is the overall depth. Overall depth minus effective cover, we get the effective depth. So this is all the information M20 and FE415. So FC and FY we have. So first, now how we will calculate? First we calculate the XU by D. Second we have to calculate XU max by D. Then after that we have to move towards the calculation of comparison that, and we have to define the what kind of section it is, and on the basis of that we will calculate the moment of resistance. So this, please solve this question and find out that what is the moment of resistance for this beam. Now we have the second type of problem. In second type of problem is the in which we have to determine the steel area in tension, how much steel area we will provide, and we already know the cross section and the moment. Moment means load. Okay, so now this is the partial design problem. Why I am calling this problem is the partial design problem, because we have the dimensions but we have to calculate the area of steel in tension zone. So that is why I am calling that this is the partial design problem. So now in this type of problem, what data we have the size of the section, mean dimensions we have, then the what is the load coming on the beam, that is in terms of load or in terms of moment we have. Okay, and what is the grade of the material we are using, so that we also know. So these information we have in the question, and after that we have to find out the area of steel. So this is the second type of problem. So now I will discuss with you the design steps. So what is the design steps we have? So in first step we require the ultimate moment. So ultimate moment, if the ultimate moment is directly given to you, then we will skip this step number 1. Or if the maximum bending moment is only given to you, then we have to convert that value into ultimate moment by multiplying by 1.5. So this is how we can calculate the ultimate moment. So this is the first step. In second step, what we will do, in the second step we have to calculate the limiting moment of resistance. So what is the limiting moment? Well, moment of resistance means mu limiting. For that we have this formula. So this formula is that we have at the page number 96 of the code. So from there we can use this formula. So in this formula we have by using this formula we will calculate the mu limiting. After that, in third step we will compare both the values, that is the mu and mu limiting. So again on the comparison, on the basis of comparison, we will define the what type of section it is, that is the under, balance or over. If the mu is lesser than the mu limiting, in that case we will say that section is the under reinforcement section, and the tension or reinforcement we will calculate by using this equation. In second condition, if mu is equals to mu limiting, then we call the section is the balance section, and the area of tension we can calculate by using this formula. After that, if the third condition, if mu is greater than the mu limiting, then this we call the section is the over reinforced section. As I earlier told you that in such condition code doesn't allow the design. He asked that you have to redesign the section. Redesign the section means you have to increase the size of the section, or you have to go for the doubly reinforcement beam. So this is the we have. So this is how we can. After that, once we calculate the area of steel, after that, if the section is under reinforced or and balance section, then we calculate the area of steel, and after that we have to calculate the number of bars, whatever diameter of bar we are using. If we are using the A5 5 diameter bar, then the area of that bar, and we divide the AST by that A5. So that is how we get the number of bars. So these are this is how we will partially design this type of problem. So now I will take the numerical. This is even numerical. We have in this numerical, we have a rectangle beam of 20 centimeter wide. 20 centimeter wide means 200 mm width and 40 centimeter deep up to the center of the reinforcement. Up to the center of the reinforcement means this 40 centimeter, this 400 mm is the overall, that is not the overall depth, it is the effective depth. Okay, and we have to calculate the area of reinforcement, and the moment which is given to us, that is the 25 kilonewton into meter. Grade of the material is the M20 and Fe415 is using. So now we have to find out the area of tension reinforcement. It is easily, now first we write the what given data we have. So now we can see the what given data we have. We have the given data like width we have, effective depth we have, 20 centimeter means 200 mm, effective depth 40 centimeter, 400 mm we have. A moment, only moment word is there, so we can say this is the maximum moment, this is not the ultimate moment. So M is, we have 25 kilonewton into meter, M20 and Fe415 grade of material we have. So we can easily say that this is the characteristic strength of the concrete, and this is the yield strength of the steel. So these information we have in the question. Now we start the solution. So first step, we have to convert the M into the MU. It means we require the, because for the comparison to find out the area of steel, we require the two values, that is the MU and MU limiting. So first we have to calculate the ultimate moment. So ultimate moment 1.5 times of maximum bending moment. So maximum bending moment is already we have, that is the 25 kilonewton into meter. So if I multiplied it by 1.5, then I get the ultimate value of the moment, that is the 37.5 kilonewton into meter. After that we have to calculate in second step limiting moment value. So that is the, for that we have this formula. We have all the values in this. FCK we already know, XU max by D, because we know the grade of steel. So we can easily see, we in this question we have the grade of steel, that is the Fe415. So for that we know that XU max by D equals to 0.48. This value you can see at the page number 70 of the code. Page number 70 of the code. So this is how now XU max by D we know. XU max by B and D already given to us in the question. So we can easily calculate, and when we are, while we calculating it, we can find out that we are putting all the values in Newton and mm. So the moment limiting we are getting in terms of Newton into mm. Earlier we are having the MU is in 37.5 in kilonewton into meter. So again we have to convert this value into kilonewton into meter. So we converted it, and we can find out this is the 88.30. So this is the MU limiting value we have. So now after that we have to compare both the values, and if we compare both the values, then we can say that 37.5 and one is the 88.30. So we can easily say that MU limiting is the greater and MU is the lesser than the MU limiting. So in that case we can easily say that the given section is the under reinforced section. So for that area of the steel is which we require to calculate the for required in the tension zone, that is the, we have the formula. So now we put the values. FCK we have, Fy we have, we already know that values in Newton per mm square. Mu we have already calculated 37.5 kilonewton into meter. FCK we already know, BD we already know. So we can easily calculate it, and we can easily find out what is the area of steel, that is the 280.15 mm square. While calculating, you have to take care of the units. You can see here we are putting FCK Fy in Newton per mm square, we are putting B and D in mm, but Mu we have the 37.5 kilonewton into meter. So that is why we have converted that value into Newton into mm. So that is why I have multiplied this value by 10 raised to power 6. So while you are solving such problems, you have to take care of the units. Okay, so this is how we have completed this question. We have getting the area of steel. Now we have the number of bars we have to find out. So first we have to decide what diameter of bar we can use in here. So it is up to us that what diameter of bar we are using here. So that is, if I am using the 12 mm diameter bar, so in that case the A phi equals to pi by 4 of 12 mm square, and then number of bar AST or A phi, so can easily I can say the 2.48 bars. So I have to provide 3 bars of 12 mm diameter. So this is the end of the question. We have to, in which we have calculated first mu, that is the ultimate moment, then we have calculated the limiting moment value, that is the mu limiting, and we have compared and we have decided what type of section it is. If the given section is the under reinforced section, balanced section, and over reinforced section, so on the basis of that we have calculated the area of steel, and then we have provided we have calculated the number of bars. So these are the steps. This is how we can do this. Now I have one problem for you. This is the one problem I have, in which you have to calculate the area of steel of grade Fe 415 required for a section of 250 mm width, and the overall depth is the 500 mm. Okay, so and effective core also given to you, that is the 40 mm. In this you are using the M20 grade of concrete, and the ultimate moment is given to you, that is the 146 kilonewton into meter. So now you again, before solution, you have to write the given data with units. So I can say B, D, D dash, and all the values we have. Now in this question we need not go to for the first step, because mu we already have. So now we start this question from the step number 2, in which we calculate the mu limiting, then we compare the mu and mu limiting, and after that we will calculate AST and number of bars. Okay, so this is the hierarchy of in this question. We will skip this step number first. So this is the second type of problem we have. After that, now I will take the third type of problem. In third type of problem, which I call the design problem. The design problem, in which we don't know the section size, we don't know the area of steel. Now we have to calculate the dimension size and area of steel, and after that we will provide the reinforcement area of steel, and then we provide the number of bars. So now what information we required? We required the how much is the load or bending moment coming on that beam, and the what is the grade of the materials which we are using in that, and the what is the span of the beam. Such information we required to design in this beam. So now I will take the design step. So in design step, in first step we have to calculate the mu. So again mu, for that we required such information. So first we will assume one depth. So we assume one depth, that is the basis of the effective span. If we have the LE is the effective span, we already know. So that LE by 12 to LE by 15, generally we take the overall depth. Okay, after that we will calculate the width, and on the basis of width we will calculating by using this step D by 2 to D by 3. Okay, first we calculate the overall depth. We will take one on the basis of the exposure condition, we will consider the effective cover. So in general consideration, we will take the 40 mm depth effective cover to the reinforcement in the beam. So in that case we can easily calculate the overall depth on effective depth, and if after calculating the effective depth, we can easily calculate by using this one D by 2 to D by 3. So this is the we have. Now how we will calculate the effective span? So effective span, that is, this is how we can calculate the clear span and the width of the support, or clear span and effective depth. The minimum of these two we have to take the effective span. Okay, after deciding the dimensions of the section, we have to calculate the dead load or self weight, that is we calculate by using 25 B into D. 25 is the unit weight of the RCC. So 25 kilonewton per cubic meter is the unit weight of RCC. We multiplying by B and D, so we can get the cell weight in terms of kilonewton per meter. After that we have to calculate the total weight, cell weight we have calculated, and live load, what is the coming on the beam, it is already given us in the question, so we can easily calculate the how much is the total load coming on the beam. After that we will calculate the maximum bending moment. That depends what type of beam it is. If it is the simply supported beam, then we can WL square by 8. If it is the cantilever beam, then we can say WL square by 2. So this is how we can calculate the maximum bending moment, and then we multiply it by 1.5 and this maximum bending moment, and we will get the ultimate moment value, that is the mu. So this is the step first, in which we calculate the mu limiting. After that we have to calculate the limiting moment of resistance factor, that is the Ru. This is this formula for that. Ru is the 0.36 FCK XU max by D bracket 1 minus 0.42 XU max by D. So we know all the values, FCK from the grade of steel, grade of concrete, and XU max by D from the grade of steel. So by knowing the grade of the materials, we can easily calculate the Ru. After that we have to check that whatever the D we have assumed in step 1, that is correct or not. So for that we will calculate the D required. For this we have this formula. So in this formula. Mu we have already know from the step 1, Ru we have calculated in B in step number 2, and B we have assumed in step number 1. So we know all the values and we can calculate the R required. Now if the R required is lesser than the earlier we are provided the R, if this D required is lesser than the we provided D in the beginning, then it is okay. If this D required is the higher than the as D provided earlier, then we have to again go to the design step number 1 and again repeat the step 1, 2 and 3. Okay, so this is how in step number 4 we have to compare the both the values D required and D assumed in step number 1. Okay, and if the assumed D is lesser than the D required, then we have to redesign and comes to again step number 1, 2, 3. After that, if the D assumed is the greater than the D required, then it is okay, then we can move for the further steps. After that, now we have decided the dimensions. We have verified that the assumed dimensions is sufficient. After that, we will calculate the area of steel by using this formula. Okay, after that we have to check as per the IS 456 the minimum reinforcement is how much is the minimum reinforcement we require. So for that we have this formula, that is the step number 6, and then we have compare both the values AST and AST minimum, and on the basis of that we can calculate the number of bar. If the AST is the lesser than the AST minimum, in that case we will all provide the AST minimum, or if the AST is greater than the AST minimum, then we calculate the number of bars by using the AST. So overall we will take the maximum value between the AST and AST minimum. So on the basis of that we will calculate the numbers of bar. So this is how we will design the beam. Now we will take the problem. How we will design the singly reinforced beam. So now this is the one problem we have, that a rectangle reinforced concrete beam we have, which is the simply supported beam, 2 masonry walls of 230 mm thick, that beam support by this masonry wall, and 6 meter apart. It is center to center, means it is the LE, and the beam is carrying an imposed load of 50 kilonewton per meter. Imposed load means it is the live load it is given to us, that is 15 kilonewton per meter. We have to design this beam, and we have the grade of materials M25 and Fe415. Okay, so now first we write before designing we write the design, what are the given data we have. So BW, that is the width of the support, 230 mm we already have. Imposed load we have, that is the 15 kilonewton per meter. After that we have the effective span, center to center distance we have, that is the LE 6 meter we have already have. After M25 grade of concrete we have, so FCK characteristic strength, that is the 25 Newton per mm square, or Fe415 steel we have, so Fy and XU max by D we have. So these are the information we have. Now for this we have to design the beam. Now in first step we have to calculate the ultimate moment, that is the Mu. So for that we required to assume the value. So LE we already given in the question, so we can take the D. So 500 mm if I take effective cover, if I am taking 50 mm, so now I getting the effective depth. So this is my assumed value, okay, on the basis of this ratio. Okay, after that width of beam, on the basis of small d, it should be 225 to 1, so I am taking the value higher side 250 mm. Okay, so 250 mm value I am taking in this beam. So now I am taking the size of the beam in this section, that is the 250 mm by 500 mm. This is the size of the section. This is the small b and this is the capital D. And effective depth is the effective, or I am using 50 mm, so effective depth for me is the 450 mm. This is the dimensions I have assumed in part A of step 1. After that now I am calculating the loads, how much load is coming on the beam. So first I am calculating the dead load. So dead load is, I know 25 B into D, 25 unit weight of RCC. So I can easily calculate 3.15 kilonewton per meter. So now you have to look at this, that 25 is in kilonewton into meter, B and D we have assumed in mm. So we have to convert that value into meter. So that is how we get the 3.125 kilonewton per meter is the self weight of this beam. Now we calculate the total load. Live load we already know 15 kilonewton per meter, that is already given to us. So we can easily calculate the total load, that is coming 18.125 kilonewton per meter. After that, determining this, we have to calculate the maximum bending moment. So maximum bending moment is the W total L square by 8, because this given that this beam is a simply supported beam. So W total we have calculated 18.125, L is the 6 meter, it is already given to us in the question. So maximum bending moment we can easily calculate, that is the 81.56 kilonewton into meter. After that, now we have to convert this maximum bending moment into the ultimate bending moment. That is, for that we have to multiply mx by 1.5. So we can easily get the ultimate bending moment, that is the 122.34 kilonewton into meter. So this is the ultimate moment. This is the step number 1. Now we have to calculate the limiting moment of resistance factor, that is the RU. We have the formula, we have the FCK and XU max by D values already we know. So we can easily calculate that RU is the 3.45 Newton per mm square. Now after that, after calculating the RU in step number 3, we have to calculate the D required, that how much D we required. So for this moment and for this factor value, so now we can calculate the D required by using this formula, under root of mu over RU into B. So mu we have calculated in step number 2, RU we have calculated in step number 3. Mu we have calculated in step number 1, RU we have calculated in step number 2, and width we have assumed in step number 1, that is the 250 mm. So we put all the values and we have calculated 376.56 mm we are getting. And actually D, now we have to compare in step number 4. So we can easily see that earlier we have assumed the value small d, that is the 450 mm. And we required 376.56 mm, so it means it is okay. We have taken the higher side for the safety purpose, so that is why we are taking. So we will consider this value, that this is the approved value. Now we can move for the further step. So now whatever dimensions we assume, that is the 250 mm by 500 mm is correct. It's correct. Okay. Now I will calculate the area of steel. So area of steel, again we have the formula. I can have all the values which required in this equation. I put the values and I get the AST. Now I have to calculate in step number 6 AST minimum, how much minimum reinforcement we have to provide as per the IS 456. So that is 0.85 B into D over Fy. B and D we already know, 250 and 450 mm, and 415 is given to us, that is the 415 Newton per mm square. So easily we can calculate the minimum reinforcement. Now maximum value we have to take in between AST and AST minimum. So maximum value is the 863.35. So now we calculate the number of bars by taking this value 863.35. I am taking the bar is the 20 mm diameter. It is design problem, so it is up to you that whatever diameter you want to take, you can take easy. If you using 12 mm diameter, then the number of bar will increase. Then it will affect the spacing between the reinforcement. So but here you can take the diameter. So here I am taking the 20 mm diameter. So phi equals to A20, that is the pi by 4 20 square, and that is value is the 314.16 mm square. After that, number of bar I required. So number of bar I required. So in that case, number of bar I required. So that is the number of bar AST over A5, that is the 2.75. So for that I can say that 3 bars of 20 mm diameter I will provide in the tension zone. So for that, at the end we have to draw such cross section in which we have to give all the dimensions which we have taken, we have mentioned here. So you can see that this is the cross section of this beam, in which the size is the 250 mm of 500, and up to the center the effective depth is the 450 mm. Okay, and 3 bars of the 20 mm diameter we are provided, so which is also mentioned. So this is how we end this question after drawing this sketch, cross sectional sketch. So again I will repeat, in first step we will calculate the mu by assuming the value of B and D. In second step we calculate the RU, that is the limiting moment resistance factor RU, and by using the mu and RU we will calculate the D required. Then we compare the assumed value and required value. If assumed value is higher than the required value, then we can proceed for the step number again. Then we will proceed for calculation of steel. So if the value is not higher, then we again have to repeat the step number 1, 2, 3. Okay, till that D required is lesser than the D provided. Okay, after that we have calculate AST. AST is the then AST minimum. After calculating a comparison of both the values AST and AST minimum, we have to calculate the number of bars, and at the end we have to draw such sketch, cross sectional sketch. So this is the design of the beam, purely design of the beam. So this, now I have the one problem for you. So this is the one problem I have, in which you have to design a beam Okay, so in which limiting bending moment is given to it, means mu is directly given to you 65 kilonewton per meter, kilonewton into meter, where effective span is the 6 meter. So M20 and Fe 415 grade of materials you are using. So for that you have to design this beam. So this is the same way you have to initially you have to assume the values and then you can proceed. So this is the end in this question. So now in this we have completed the analysis and design of the singly reinforcement beam. So this is the end of this lecture.